Hey team, I'm Maddie. Welcome to Science Side Up, and today is Journal Club number 3. We are still reading our paper on heat problems. That's like heat problems part 1 from the Answers Research Journal. And the purpose of this stream is to do just kind of like a community reading and live critique of this paper, treating it as I would a real science paper. Um, and we've seen that that's not going super well, because it just doesn't work. This paper and the Answers Research Journal in general is not written to be a scientific journal. It's written to be a popular level, like a popular level thing that's kind of like cosplaying as a real journal. Um, and yeah, so it's just not there. And so we're reading this Heat Problems Associated with Genesis Flood Models, Part 1, Introduction and Thermal Boundary Conditions. So we've read the abstract and the introduction, the interior temperature and structures of the Earth. And now we're going to get onto ocean temperatures. And this is actually the section I'm kind of excited to see because I want to see how our author here, how does he reconcile using this oxygen 18 data for these purposes, but not accepting that we have oxygen 18 data that goes back like tens of millions of years. And so why is some of the data good and some of it not? So I'm really hoping that gets addressed here, and so we can chat about that. Okay, so let's just go ahead and jump straight into it. Thank you guys so much for joining. I hope we can have a lovely chat over in the like Premiere chat. Yeah. All right. So ocean temperatures. Considerable geological evidence is available relating to Earth's past ocean temperatures and ice cover. That is true. Would love to see a citation. The temperature data comes from marine deposits from the whole span of the geological record, notably from the Phanerozoic fossil shells. Would love to see a citation. I actually don't know if that's true off the top of my head. I don't do paleoclimate. This sounds on the face of things right. Based off of my very limited knowledge of paleoclimate, that sounds right, but this should have a citation. The record is particularly rich for ocean floor sediment thanks to extensive ocean floor drilling programs carried out over the last 50 years, vis-a-vis the International Ocean Discovery Program, Exploring the Earth Under the Sea, IODP, cool, 2017. Hey, that's a thing we could Google, but it's not a citation. And its earlier incarnations. There should be a citation there because these big projects tend to have like, though there's like they have like one big paper with a million authors that you're supposed to cite when you're like referencing the project as a whole. The resulting data is publicly accessible via the Pangea online database. Okay, cool. He did cite, we do have a citation for that. Good. Geologically, most ocean floors are identified as Jurassic, Cretaceous, or Cenozoic, i.e., not exceeding 200 million years in uniformitarian terms. There's again that uniformitarian term coming in, which is uniquely used in creation literature, right? At least in the modern world. That is not a term I ever heard before I started debunking young Earth creationism and other pseudoscience. Although the Ionian Sea and the Eastern Mediterranean are dated from 270 to 230 million years, and we have a citation that is beautiful. This is catastrophic plate tectonics model, in which the post-flood boundary is tentatively located at the KPG, Cretaceous Paleogene interface. These stratigraphic assignments correspond to mid-flood and post-flood times. Goodness. In other flood models, the correspondence of ocean floor development with flood chronology varies according to where the flood post-flood boundary is placed. See section 3 for further discussion of alternative flood models. So that's going to be really interesting because if they're talking about there's a phenomenon that happens in the ocean floor, and that has to do with the ocean floor is where we see these bands of um, magnetic the magnetic field, the Earth's magnetic field, first going in one direction, then another. So when the ocean floor, right, we've got two ocean plates and they spread apart. And as they're spreading apart, new material, basaltic material, comes up and is solidifying, making new ocean crust. That material has iron in it, right? And in the absence of any other strong magnetic field, the iron will align itself along the Earth's magnetic field. Um, and so we see bands. This is how we know about the Earth's past magnetic field reversals, um, where sometimes the Earth's magnetic field it weakens, like it's doing right now. It weakens, it shuts off, and then it reappears upside down. And there's a whole field that studies this. It's called um, paleomagnetism. Is a field in geophysics. Um, and that's like the study of it's a very useful thing because um, you can use if you know the position of the Earth's magnetic field, like its alignment at a certain time, and you know a rock was made at that time, and you know where you found that rock now, you can actually like reconstruct based off of the magnetic field, how the ferrous material, how the magnetic things that can be affected by magnetic fields, how that ferrous material in the rock is aligned, tells can tell you where that rock formed, which is really cool. So that's like a whole field in geology. Anywho, and so if all of this ocean floor is formed during the flood, then you're having to have like multiple of these field reversals um, back and forth and back and forth and back and forth all throughout that year. And that sounds bonkers and is something that would need to be explained in an adequate or in a complete flood model. Anyway, the most widely used temperature and ice cover indicator is the oxygen isotope ratio. So, how much oxygen 18 do you have in the water versus oxygen 16 in marine fossil shells and in ice? Hence the term oxygen isotope paleothermometry. That's fun. This has been completed over the last 20 to 30 years by complemented, over the last 20 to 30 years by other temperature indicators, including fossil shell magnesium calcium ratios, coral. Oh no, what is SR? I should know that. Strontium? Calcium ratios, biomolecular indicators, and clumped isotopes, which are reviewed in the next part 2 in the series. That's lovely, but this still needs a citation here. So far, like the citations in this are just sloppy. Like this wouldn't be acceptable as a like graduate paper, right? Or even an undergraduate paper. This is the citations here are really sloppy. Let alone in the in the peer-reviewed literature. Anywho, but we make sure we always cite our young Earth creationism papers. Okay, principles of oxygen isotope paleothermometry. Um, by the way, this is another reason why this is not a, a scientific article, right? Uh, all you have to do for a science article is if, hey, I want to use this oxygen 18 isotope information, cite the paper, they'll explain all the details. But that's not what this is doing. That's why this is science communication. This is explaining the whole process to an uninformed, non expert audience, which is why it's inappropriate for Answers Research Journal to be called a research journal because it's not. Okay, oxygen has three stable isotopes, oxygen 16, 17, and 18, with respective molar abundances on Earth of blah, 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 of mostly oxygen 16 with some 17 and 18. Love that we have a citation here. The bracketed numbers are the quoted uncertainties in the last figures. Great. And the oxygen 18 oxygen 16 ratio in any given sample is expressed via the delta 18 oxygen value defined by the ratio of the sample over the ratio of the standard minus 1 times 1,000. Cool. Love that for you. Love that journey for you, where R represents the oxygen. Okay, sorry, what I just said. It's quoted in parts per thousand or per mil, signified by the symbol percent, so like with the double zero on the bottom. The standard for that value for marine fossil shells is known as the VPDB. That's a terrible acronym. I hate it. Vienna PD belemnite for water, and VS MAO, Vienna Standard Mean Ocean Water. There's a small offset between these standards. Cool. The long-term reproducibility of the laboratory standards for carbonate, oxygen 18 values is within plus or minus 0.08, and that's of that like 1,000 like percent. Great. So it's a really stable thing that we know. Oxygen isotope paleothermometry is founded on the temperature dependence of oxygen isotope fractionation between authigenic minerals and ambient waters. Cool. This is a thermodynamic effect favoring a slightly higher proportion of the heavier isotope in the mineral than in the water, but weakening with increasing temperature. So the warmer it is, the colder it is, rather, the more oxygen 18 you'll see in a mineral versus in the water, is what that said. Hence, under equilibrium conditions, the oxygen 18 oxygen 16 ratio of precipitating carbonate and phosphate materials depends only on the temperature and on the oxygen 18 to oxygen 16 ratio of the seawater for a given ambient oxygen 18 level. Lower oxygen 18 fraction values in fossil shells imply higher water temperature and vice versa. From first principles, Urey et al. Estimated the variation of the oxygen 18 fraction with temperature to be about negative 0.176 of this 1,000th percent per degree Celsius for carbonate minerals. Then that was updated in 2014. They conclude the most extensive set of observations comes from the combination of some Latin names I'm not going to try to pronounce because I'm not a biologist, which exhibit. I'm not a biologist, and have just enough of the Southern accent that if you make me do Latin or French, oh man, it comes out. It's real bad. It's real bad. And I get embarrassed, and so I don't want to do that. A quadratic temperature dependence. Okay, that's cool. So it's talking about a quadratic temperature dependence in the 50s. They found he calculated a linear dependence, blah, blah, blah. So this is just making the estimate better. Sorry, this is reading like a report. This is good stuff to read, but you don't have to. If you were writing a review paper that wanted to cover from 1950 to modern times, I guess this would be appropriate, but that would be a hefty review paper. Oxygen isotope paleothermometry of Paleozoic and Mesozoic marine fossils is based largely on the shell of brachiopods and bivalve mollusks, belemnite guards, the bullet-shaped ends of belemnite fossils. See what I mean? This is for a lay audience. And conodons. Glad we have a citation for that. In the Cenozoic, the tests skeletons of both planktonic and benthic foraminifera make a major contribution to the oxygen 18 fraction database. Of these, the benthic foraminiferal record is the most important for reconstructions of bulk or interior ocean temperatures. Cool. While planktonic foraminiferal data is more relevant for reconstructing sea surface temperatures. Calcium carbonate fossils are the most important for scientific study. All the organisms mentioned in this paragraph produce calcium carbonate fossils with the exception of conodonts, which are made from calcium phosphate. Cool. Would love to see a citation for that. Why are calcium carbonate fossils the most important, right? Oxygen isotope fractionation also occurs when water evaporates. H2O, it's just water molecules, but specifically O18, which are heavier than the more abundant water with oxygen 16 molecules, preferentially remain in the liquid phase, the resulting vapor being correspondingly depleted in oxygen 18. Consequently, rain or snow resulting from condensation of atmospheric water vapor has a lower oxygen 18 fraction than the original seawater. Yeah. Condensation also causes fractionation such that water vapor remaining in the atmosphere becomes further depleted in oxygen 18. Most heat and mass transfer from the oceans to the atmosphere occurs at low latitudes, followed by transfer in the opposite direction at higher latitudes. That is true, and that's general knowledge, so you don't need a citation for that. So this is basically water tends to evaporate at the equator and then rain and snow at higher latitudes. That's kind of what this is saying. You don't often get a lot of evaporation directly out of the Arctic, right? Um, yeah, you do get lots of you do get rain and stuff in the Arctic and snow, mostly snow, but okay. Hence, atmospheric water vapor becomes progressively depleted in oxygen 18 as it moves poleward, such that oxygen 18 fraction value in precipitation decreases as the air cools. Okay, cool. Furthermore, orogenic or high altitude precipitation becomes progressively depleted in oxygen 18 as the air rises and cools. These processes are known as Rayleigh distillation, see figure 2. Beautiful. So here's the oxygen 18 water cycle. From equator to the South Pole, that's fun. Um, that's a fun upside down plot. Um, Cool. So we have like mantle, right? Crust, if you will, here. This would not mantle, I meant crust. So this is like ocean crust. So this is like depth on this x-axis here. And then the radial axis, sorry, yeah, my axes, is going to be depth. And so here's the atmosphere, and then here is like the ocean, and then here is the underlying crust. Um, and this is like the South Pole, so then we change radially like this. So we're looking at tropics, we're getting a nice atmospheric circulation. I love that we're using a figure from 1977. You could have updated it, but anyway. So this is that transport. I'm inclined to just kind of accept that this is true. These are citations from regular literature. So this isn't, he's not being deceptive or anything here. This is just how this works, which is pretty cool. I've never read this in depth before. Um, okay, so so snow and ice sheets formed from this depleted oxygen 18 water exhibit the lower oxygen 18 values at lower condensation temperatures. Despite a number of complicating factors, this effect is exploited as a paleothermometer in ice core studies. Yeah, so this is all the theory behind how we reconstruct temperature profiles from ice cores. Ice sheets today typically show an oxygen 18 fraction between -30 and -50 of that 1000%. I don't know the exact right word for that. Since water with oxygen 18 is depleted in ice, the greater the global volume of ice, the greater the inventory of oxygen 18 water ice residing in the oceans and atmosphere. Thus, when there are significant ice sheets on the Earth, such as in the last ice age, um, the oxygen 18 value in the seawater and hence marine fossils becomes a proxy for total ice volume. Yep, high values of oxygen 18 in the oceans imply large ice volumes. This effect was first established by Shackleton in 1967 and then further developed into set in the 70s, who linked those Milankovitch cycles um, to the fluctuations in oxygen 18. So we have like known stuff about how Earth's orbit works, like the predicted behavior, and then the predicted behavior of Earth's climate based off of that. I do have a video somewhere on my channel about Milankovitch cycles. And then this is supported by other evidence, by this oxygen 18 evidence. So that sounds like absolutely wonderful, predictive, and observable science to me, right? Because we have something that we can like just calculate based off of orbital mechanics that's then supported by stuff we can go dig up and look at and measure, right? Okay. The astronomical theory proposes that the variations in the Earth's orbital pattern, specifically eccentricity, obliquity, and axial precession, lead to variations in incoming solar radiation in the summer at high latitudes. Glacial intervals. Well, okay, yes, that's true, but like, okay, sorry, that's an oversimplification. It's just considering the northern hemisphere instead of like the whole globe. But anywho, um, glacial intervals are supposedly triggered when the radiation becomes too weak. Yeah, yeah. If you don't have enough incoming energy, the Earth gets colder, right? Love that supposedly. Hence the tilt of the well known and much cited title, excuse me. Uh, Hayes, Embry, and Shackleton, 1976 paper, Variations in the Earth's Orbit, Pacemaker of the Ice Ages. That's really cool. I actually have never read that paper because this stuff is like old enough. This is old enough knowledge to be like general knowledge in all of planetary science, geophysics, atmospheric science. Yeah, because of the apparent explanatory success of the astronomical theory, it now serves as a ruling paradigm in climate research and is often used to calibrate climate data chronologically. Cool. Notably, isotope records in deep sea cores. However, this theory suffers from serious methodological flaws. Oh, I would love to see what those are. Um, I might need to I might need to download those papers. Yeah, I'll do that offline, but, I gotta look at that. Hold on, I'm gonna can I use a highlighter? No? Oh, you won't let me highlight text in this, that's very upsetting. Silly Acrobat. Um, I've gotta read those because we're finally getting to a climate thing I know stuff about. In summary, assuming the uniformitarian chronology, the scientifically accepted, right? The most critical problems are orbitally induced changes in solar radiation are very weak, especially the 100 uh, Ka. I actually don't know. I don't know what that is. Eccentricity cycle, which appears within the astronomical forcing paradigm to have dominated climate variations over the last. Uh, that's like 1,000 Ka. Yeah, like 400,000 years? Yeah, sorry, the 100,000 year eccentricity cycle. Yeah. Ice age cycles are in the phase between northern and southern hemispheres, whereas the astronomical theory predicts the opposite. I don't think that's true. No, when the northern hemisphere cools, the southern hemisphere should warm up. That's not true. That's not how that works. Um, uh, uh, yeah, that's just not how that works. Uh, this because we still have seasons, right? You're still gonna have summer, winter, right? Even in an ice age. It's just like less noticeable. Anyway, um, and also like my guy, like the Earth is like you're not gonna get an ice age in the northern hemisphere and like balmy warm weather in the southern hemisphere because information heat transfers across the equator, right? nature abhors a vacuum, but nature also abhors sharp gradients, right? It's going to work to even those out. Yeah. Causality, the warming which terminates a glacial interval sometimes proceeds by several thousand years, and the change um, in solar radiation supposedly causing it. I would need to read that citation. That doesn't sound right to me, but the assumed age of 700,000 years for the magnetic reversal boundary used. I don't know what that is, because the Earth's magnetic field reverses much faster than that. On Using constructing age models for the analysis of Hayes, Embry, and Shackleton has since been revised significantly upward. Okay, I don't actually know what they're talking about here. So what? Well, let's look this up. Let's look up this magnetic reversal boundary. What is this? Let's look that up. So let's stop sharing that and go to Google. Yeah. Boom. Allow. Oh, sorry. I found the catastrophic plate tectonics paper there. Here we go. Please enjoy. Okay. Cool. Yeah, what is this? A geologic event approximately every 2.8 million years when the Earth's magnetic. Oh, okay. When a geomagnetic reversal from normal polarity. But not, this isn't Gauss. Okay. Okay. Well, accept all cookies from Springer. Okay. This is an article from 2020. A development of the age model for sedimentary and volcanic sequences and help decipher the dynamics of Earth's magnetic field, the structure of the geomagnetic field during the MB geomagnetic reversal remains controversial due to its complex field behavior. In this study, so this is a thing in paleomagnetism where there was a geomagnetic reversal. Okay, sorry, what I know about geomagnetic reversals is that they happen pretty commonly, and I guess this is just a specific one that maybe was discovered earlier than other ones. We defined an average stratigraphic position of, oh, and then you can use that to like date rocks, because if you can find that reversal in rocks in like continental crust, right, then you can use that. Oh, okay, before and after. Oh, okay, so that is really useful, because usually we see magnetic reversals in like the oceanic crust, right, which is younger. Cool. Okay. Um, okay. Okay. Sorry. I'm understanding what this is. So this is going to be a specific geomagnetic reversal that was found that you can use like globally in different types of crusts to kind of identify time periods. Gotcha, 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 gotcha. Okay, we won't jump into like all the details of that. Cool. Okay, so let's go back to the paper and see what this has to say. Um, so I think he's just saying that uh, okay, so this magnetic reversal, which was used in that 1976 Hayes, Embry, and Shackleton paper, has been changed, which is cool. Um, I don't know how they used it in their paper. Should we just go to this Hayes, Embry, and Shackleton paper? but by the way, this like 700,000 years down back up to like a million years, right? Uh, I'm trying to think of what magnetic field reversal has to do with an ice age. um, I don't know. Uh, they base their climate reconstructions on Platonic rather than benthic formifera, since the former are much more likely to be affected by local short-term temperature variations. How could Hayes and co-authors be sure that they measured oxygen 18 fraction values represent globally synchronous signal? Um, and Ord 2007 claims that the uniformitarian paradigm in the field continues as a reinforcement syndrome. And Herbert 2016, that's a young earth creationism paper, concludes that the data sets have evolved over time, thus calling into question their supposedly objective nature. So we probably need to go in and read those papers. But what I'm hearing is okay, so let's address these problems. Um, so one, uh, um, you don't need much change, like this is something that actually people struggle to understand about uh uh like about incoming global energy. A small change, right, in say temperature, right? So this is that incoming solar radiation, that incoming energy from the sun. A small change in that, when it is that small change added up, right, multiplied by the size of the earth, not divided by it, right? It's a small change in incoming solar radiation multiplied by the whole size of the earth, right? Um, can turn into a big change for planet Earth. So a small change in incoming solar radiation absolutely results in really big changes um, felt here on planet Earth. You can figure that out with just partially because um, that the black body spectrum, which is what we're talking about with this stuff, is dependent on temperature to the fourth power, right? And so a small change to the fourth power, right, is big. Right? I don't know a way to put that. And so you hear the same argument in like anti-climate change pseudoscience, because they're like, how can such a small change and blah result in such a big temperature change? And I'm like, a good analogy, right, is it doesn't take much arsenic proportional to a human body to cause major problems, right? The amount relative to the thing it's affecting um, depends on a lot of factors, right? So, uh, um, yeah. And it doesn't take a big change in like global average temperature to cause big changes in the weather that we experience, right? This is again a thing I talk about with climate change deniers is okay, or not even deniers, but as a good way to explain stuff, right? So people will ask me a lot, what's the big deal in a 1.5 degree Celsius change? That doesn't sound like much, right? And my answer is, okay, we're not talking about the average temperature that you experience on planet Earth. Excuse me, you experience walking around. Of course, if that went up by 1.5 degrees, um, you know, that's not going to change much. You're right. But that's not what we're talking about. We're talking about like the type of temperatures that you can measure from space. So for example, the difference between pre industrial conditions and the last ice age, the peak of the last ice age, of global average surface temperature was 4 degrees Celsius, right? And that took tens of thousands of years to change, right? So, and we've warmed 1.5 degrees in like 150 years, right? So that's terrifying, right? That's a huge change in what we experience here on the surface. Um, so the orbitally induced changes in solar radiations are very weak, doesn't matter, right? It's enough, right? Um, okay, ice age cycles are in phase between northern and southern hemispheres. Of course they are. um, uh, so so let's just use axial tilt. I go over all of these in my Milankovitch cycle video, but let's just talk about axial tilt. That's going to be the easiest one to visualize right here and now. So I have Earth, right? And Earth, do I have a ball within reach? No, of course I don't. Why would I have that? Right? So Earth isn't straight up and down, right? We have a tilt of like 23 degrees, right? And if we were straight up and down, we wouldn't have summer and winter. It would be the same temperature. We would have the same type of weather all year round, right? And so uh, if I tilt more, right, I'm going to have more extreme winters. And then will I also have more extreme summers? Yes. But both the northern and the southern hemisphere will feel that, like at in the global average, they'll feel those same swings. Um, and so yeah, we'll swing from like really cold to really hot, right? Whereas if we were more tilted, right, or more straight up and down, we would have more moderate seasons, right? If our eccentricity increases, and so anyway, so I use the axial tilt one there to give an example of why we would expect these orbital mechanics to affect the northern and the southern hemisphere in the same way, right? The idea that we could have an ice age in the northern hemisphere, but again, abnormally warm weather in the southern hemisphere is bonkers because the hemispheres talk and nature abhors non-equilibrium, right? everything about everything about our atmosphere moving is trying to get an equilibrium state, right? We're trying to have equal temperature across the whole earth. That's what all these natural processes want to happen. Anywho, so this two statement is bonkers. That is an insane thing to say, and honestly demonstrates a deep, like, that is like middle school question level, right? This is a deep lack of understanding. To again to think, yeah. I would need to see the data on this causality. Uh, the warming, which terminates a glacial interval, sometimes proceeds by several thousand years. The change in solar radiation supposedly causing it. Again, I want to see. I want to see that. Um, and uh, the dates shifted is what I'm taking away from point four. And like the dates becoming more precise doesn't necessarily undermine the fundamental theory, right? Like, um, and so I'm skeptical of that. Uh, but let's go. You know what? Hey, we've been going 38 minutes. I'll probably go about another 20. Let's go take a look at this Hayes, Embry, and Shackleton paper. Um, so let's get the citation and we'll go pull up the paper. Should be open source because it's old enough. So Hayes, Embry, and Shackleton. By the way, there's a crater on the moon that's named after Shackleton. Shackleton crater. It's like on the South Pole and is a proposed site for future moon landings. Variations. Okay, this is the pacemaker of the ice ages. Article in Science. Edit now. Oh, you want me to like buy Acrobat? We're not going to do that. Variations in Earth's orbit. Okay. Pulled up Google Scholar. I'll share that screen. Um, hello, my head got big. Okay. Share screen. Boom, boom. Allow. Here we go. Variations in, oh my gosh, I've already forgotten the name of it. I have the short-term memory of a goldfish. Earth's orbit. Orbit pacemaker. There we go. The concealed pacemaker. Okay, yeah. Cool. For 500,000 years, major climatic changes have followed variations in obliquity and precession. Absolutely. Um, okay. Three indices of global climate change have been monitored in the record of the past 450,000 years in the southern hemisphere ocean floor sediments. Beautiful. Over the frequency range of 10 to the negative fourth to negative for fifth cycle per year, climatic variations of these records is concentrated in three distinct spectral peaks at periods of 23,000, 42,000, and approximately 100,000 years. These peaks course, yeah, so this is, you would just do a power spectrum analysis. How do these change? And find these peaks, and then we can associate those peaks to dominant periods of Earth's solar orbit. Yeah, so cool. Um, Okay, it is concluded that changes in Earth's orbital geometry are fundamental causes of the succession of quaternary ice ages. Yeah, so this is a very, very important paper in like history of science sense. This put together these Milankovitch cycles to these tied these known orbital mechanics to cycles in climate. And this is again, we have observed cycles in climate based off of paleoclimate data, known orbital mechanics stuff, and then we can there's a easy physical mechanism behind it. Um, so that's really cool. Oh, that's just the abstract. Let's take a look at the PDF of this. And we're just gonna do a quick like roll F for um, that weird magnet thing they're upset about. I feel like this is sort of a mountain out of a molehill, or you know, like, of course, parts of this theory have been updated and refined, because this is from the 70s. But that doesn't mean that the core thing behind it isn't true, right? Um, so we're gonna look for, okay, Control F. There we go. Mhm. Okay. Oh shoot, it's still Control Fing. Why are you being slow, friend? Doo-doo-doo-doo. Ooh, here we go. Okay, the age of the boundary between stage 12 and 11 was taken from this paper, which estimated it at 440,000 years in an equatorial Pacific core by assuming uniform accumulation between the core top and the magnetic reversal, marking this boundary. Okay, cool. So this is like one of their data point. They dated using this number. It's been refined. That doesn't sound like a major problem. Um, you know, it just doesn't. Like it doesn't negate the core theory. Um, it maybe updates a number, which probably honestly makes it more precise, like makes it match closer. I don't know that for sure, obviously, because I just glanced at it, but that's not a real. I would need to see the real criticisms of that. So I should probably read those specific papers. So we can do that in a future journal club. That would be fun. Okay. Okay. Uh, so basically, some of their dates could have been better, and are not necessarily measuring like global things. So that sounds like they're using the best data available to them at the time, you know, and all data sets have known issues. So I'm not going to worry about that. Um, and oh, this is something I've heard before. Again, this comes up in climate change, when so this idea of this reinforcement syndrome. Um, the data sets have evolved over time, this calling into question their supposedly objective nature. This idea that we added more data to something old and the new data supports our theory even better. Um, climate change denialists do this all the time, where they're like, look, they added more data and then the warming became more apparent. Sus much? It's like, no, my guy, we made a prediction based off of a limited data set and it was reinforced by the more advanced data set, right? That's what happened. That's it. That's all that happened. Yeah. So anyway, we'll have to read that or paper. Okay. Okay. When significant ice sheets exist on Earth, other climate indicators are needed to quantify separately the contributions of temperature and ice volume to oxygen 18 fraction values, notably paleontological and geological evidence of lower sea levels and the existence and extent of ice sheets. Cool. Um, so, and then in a flood scenario, rapid changes in ocean conditions are expected, which may invalidate some conclusions based on the usual uniformitarian assumption of temporal near equilibrium of oceanic levels. Detailed consideration of this issue is beyond the scope of this article. Okay, I would love to understand. So, right, in general, we don't have a good reason to think that those oxygen 18 levels are going to vary much on short periods of time is what that's saying. And this is saying like, but what if it was in a flood? I would need to see this full detailed consideration, right? We would need to how are you proposing? What are you proposing that oxygen 18 levels could change significantly in short periods of time, right? And how would that appear? How do you predict that to appear in the data, right? What would that look like? Is what I would need to see to take this seriously. So this isn't because this is just saying, but who knows what happened if there was a global flood? And that's not acceptable, right? That's not an appropriate answer. Because we need to give a like testable hypothesis, right? So that's not a valid critique in my mind because there's not. But in a global flood, there would be XYZ, and look, in these locations we see evidence of XYZ, right? That would be a valid critique, a valid criticism, not basically who knows what would happen if we added magic to the system, which is what this sounds like to me. As anticipated by Urey et al. In 1951, several factors complicate the use of the oxygen 18 as a proxy for seawater temperature. These are summarized by Grossman 2012 as disequilibrium precipitation of biogenetic carbonate. Disequilibrium, so the calcium carbonate or whatever in biological stuff not being deposited equally. Um, that's what that sounds like to me. The consistency of seawater, oxygen 18, um, and that's going to be there's probably an assumption built into those paleoclimate records that is, let's assume oxygen 18 is equally mixed, like planetary wide, and there's going to be like places where that's not true, right? But is it not true in a significant way is the question, right? Kind of thinking about that like ice cream. So think about it like a moose tracks, right? Um, am I equally likely in every bite of moose tracks to get a little peanut butter cup, right? Right. So let's say every bite I expect one peanut butter cup. Sometimes am I going to get none? Sometimes I'm going to get two, but usually do I get one? Yes. Then that's kind of the like, okay, so then good enough for government work. Let's say it's equally distributed. Right. That So making that assumption of equal distribution doesn't disallow for small local variations, right? But it does say, I'm not gonna dip my spoon into my moose tracks and sometimes get none and sometimes get 50, right? We can have small variations are okay with, and those assumptions still be valid. I hope that makes sense. Okay. Ecological influences, spatial variability versus temporal trends, and the preservation of the record through geological time. Okay, cool. And then again, every data set has problems. Pointing out even real problems with the data set doesn't mean that that data set isn't the best we have. And like, absolutely, you should understand what type of uncertainty each data set brings in, right? But if you're waiting for a perfect data set, then you'll never do science, right? Anyway, here are the major sources of uncertainty and complexity will be considered. Okay, so we're going to go to the preservation issues. He's going to address all those other issues as we move forward in the paper. But I've been talking for almost an hour and I want to reheat my coffee and say hi to my baby. You guys are great. Thank you so much for joining me for Journal Club number 3. Hope to see you soon. And I hope you're having just a wonderful day. Okay, bye team.